Hello, geometry. Sorry I couldn't be in class today. My son is home sick with the flu. I'm staying home to take care of him. Today we're going to be talking about a few things that I would like to have covered today if I was there. We're going to be in section 4.6, which is a new section, but we're going to be mixing a couple things from the previous sections together. There's a couple properties I said I want to cover today, and then we'll get to some new actual theorems today and a couple of vocab terms. Now, in order, what I'd like to actually cover, and I know this is going to seem a little weird, I would actually like to cover a couple of proofs first. It seems a little silly. I do want to do a couple examples of proofs of using some of the new properties we've had, and do some weird examples that we haven't seen for a while, or possibly ever, where we're going to do some proofs where we're going to prove that triangles are equal, but actually in one of the examples I'm going to do, there's actually a couple different steps that we haven't seen before, so I do want to show you that. Now, the other thing I want to cover is, like I said earlier, we have two new theorems today. These are based on isosceles triangles, so we're going to be messing with a specific type of triangle again. And then we have a couple of vocab words that I want to cover. But again, I'm not necessarily going in that exact order today. But again, all this information is found on page 285 of your textbook in section 4.6. So if you want to follow along in there, you can. But again, I strongly recommend that you take notes today. I will post this to my website during the day. But as of right now, it's what you're seeing is kind of live until I post it later on today. Again, if you have any questions, I'll be back tomorrow. Now, let's jump right in. Let's talk about some of the notes that I want to cover. So let's jump right in. Let's actually do a proof about triangles being congruent to each other and using some of the new properties. Now, if you're looking at my picture here, obviously we have a couple things. We're given two objects here. We're given that two angles are actually equal to each other. They're congruent to each other. And we're also given that two walls are parallel. Those are the parallel symbols. That's the little arrows, the pink arrows. Now again, like we said earlier last week, parallel implies that certain angles on a picture are equal to each other, like alternate interior. We'll look at that. But the goal in this problem is to prove that two walls are equal. In particular, we're trying to prove that FH is equal to JG. That's what we're going to try to prove. So this one will actually require an extra step than just proving that the triangles are equal. So we'll get to that as we go through this proof. Now let's actually get started. So when we start a proof, again, when you start a proof, you do have to write all the givens first. So on line number 1, we're going to write that angle F is congruent to angle J. And we're also given that FH, the wall, is parallel to GJ. And again, parallel does not mean that those two walls are equal in size. It just means that they're parallel to each other. So there's certain angles there. But again, the reason here, this is a given. So we're going to do an actual full-on two-column proof, not just a flow chart. Now, if I'm going to make the markings are already on the picture. So certain angles there are equal. Let me mark that. So this angle here, that's angle F, is equal to angle J. So we do have one mark in each triangle. There's two triangles. So again, we do need to find 3 markers and it has to spell one of our correct acronyms. Now, in line 2, we always reserve that line on a proof to be something that is obvious from the picture. Something that's obvious is the reflexive wall in the middle of the picture. So that is wall GH is equal to itself. GH. And again, the property I said earlier, that is the reflexive property, where you set an item equal to itself, but again, it's the reflexive wall. Okay. So now I have 2 markers in each picture. The last thing I'm going to do is talk about this idea of parallel. So line 3, I always state something that maybe I stated earlier in the proof that I need to redefine. So on line number 3, I'm actually talking about that the 2 walls were parallel. When the 2 walls are parallel, it implies that certain angles on this picture are equal. These 2 angles that I've marked here in green, these angles are actually equal to each other. Now the reason being is that when you have parallel walls, the alternate interior angles are the same. That was one of our first theorems we had in chapter 3. That's all parallel implies. Certain angles are equal. So I'm gonna list those angles off. So I'm gonna start with the top one. That's JGH. So angle JGH. That angle is equal to the bottom angle, which is FHG. And again, the reason I said it earlier was alternate interior. Alternate interior angles. Again, it was one of our theorems in Chapter 3. So now if you're looking at the picture, I do have 3 markers on this picture. I have 3 markers. I have the 2 angle markers, and I have a wall marker. Now the order, if you're actually looking at the picture, the order of the acronyms that we're using here, if I actually abbreviate these, this is an angle, that's an angle, and that's a side, and that's the actual one of the 3-letter acronyms that we have that justifies that the triangles are equal. So on line number 4, I can say that the top triangle, or I should say the left triangle, this triangle over here, let's call it FHG. That triangle is equal to the other triangle. We'll call that one JGH. Those triangles are equal, and the reason is by angle, angle, side. Now, they're not right triangles, so I can't use any of the new theorems we had yesterday. But they're just random triangles, and I know that the markers do spell the acronyms. Now, the acronyms we have up till this point that you can use that are possible. We could use AAS, which we just did, SSS, SAS, and angle, side angle, or ASA. So these are the 4 that we can use, and obviously we use the top one that justified it. Again, that was the new one that we learned just the other day. Now, we haven't even finished this proof yet. The whole point of this proof was to show that certain walls are equal. Well, now that we know that the triangles, the left triangle and the right triangle, are actually equal to each other, I can jump to what I'm trying to prove here. So this is the final 5th line. This is the ... line. I'm trying to prove that, therefore, that 2 walls are equal. FH, that's this wall right here, is equal to JG, that wall. So those walls are equal, JG. Now, the reason that we know that is since the triangles are equal, that forces the corresponding parts to be the same. So CP, CTC. Corresponding parts of congruent triangles are congruent. So if the triangles are equal, which we said in line number 4 that they are, then all the parts about them that are the same, the visually matching parts have to be equal. And that's these 2 walls. Those are the visually matching walls. Okay? So there's your whole proof. It's 5 lines. And again, the reason why there was 5, and it's not just a 4-line, we had to go one extra step. Not just proving that the triangles are equal, but a certain part about them is the same. Now, that was just kind of a normal proof, throwing everything together, throwing the new properties in. But the next proof I'm going to do here is radically different. There's other ways, every proof has multiple different ways of doing this. On this particular problem, there's many different ways we can look at this problem, but there's one true proof for it. We're trying to prove that this wall right here, QT, is equal to WU. So to prove that those 2 walls are equal, basically what I need to show is that this triangle is equal to this triangle. If I can get to that point, then those walls have to match because they're corresponding parts, so CP, CTC. But to get to those 2 triangles being equal, it's actually more challenging than you think it is. I can't just jump in and say it because I don't know that I have right triangles and whatnot. So we're actually going to walk through the proof of this. And it takes a little bit, kind of a strange step to actually get there. Now, let's start with the proof itself. So we'll just jump right in, and I'll explain as we go. Line 1 of this proof is starting with obviously the given stuff, that we have a lot of walls that are equal. So QR is equal to SR, which is congruent to or equal to WR, which is congruent to VR. Okay, and that's line 1, and this is our given. So we have to start with all that. And they have all the markings on the picture, so that was a terrible... Whoa. So that was a given. Okay. Now, line 2 of my proof is reserved for something that is obvious from the picture. Well, what I'm going to do is, since I have vertical angles, I'm actually going to go after the big triangle. So I'm going to prove that this large triangle is equal to this large triangle. And you're probably thinking, why would I do that when I want to get to the smaller ones later? Well, the reason why is because this will help me find the smaller ones a little bit more quickly. Okay, so I'm going to start with the bigger ones. So now, the obvious thing from the picture is having vertical angles, the little funnel system. Those 2 angles, the bigger angles, are actually equal. So on line number 2, angle QRV, I should say, is equal to the other angle, which is SRW. And again, the second line of the proof is because of vertical angles. the little funnel system. Those angles have to be the same. Okay, so let me make that mark one more time. This angle and this angle are the same. Now, I have enough markers in each triangle, the bigger triangles, to prove that the triangles are equal. The big triangles, not the small ones. So on line number, on line number 3, I can go in and say that the large triangle, triangle QRV, the big triangle, is now congruent to the other big triangle, which is SRW. And the reason being is it's by side angle side markers, SAS. And that was one of the acronyms I showed you earlier that you can use. Because again, the acronym systems that we have, in fact, if I go just back to the last slide, I wonder if I still have it up. I do. It was one of the reasons. This was the reason why. It was right here. Okay. This was the reason why. Okay. Now going back. So finishing out this proof, I now have the bigger triangles being equal. So now I can talk about the certain parts of these triangles. Namely, what I'm going to do, and I know this is going to seem a little strange, I'm going to go after, let's mark this in red, I'm going to go after that this angle here and this angle are the same. Okay, they're similar parts. They're visually matching parts of the two triangles. And how I know that, I can actually mark the other ones as well. I can mark that Q is equal to S, or they're just visually matching parts. I can mark that they're equal. So on line number 4, angle Q is equal to angle W. And the reason why it is a corresponding part. Those are visually matching parts from the equal triangles. And so the purpose of me doing this is that I want to get to the smaller triangles being equal, these two namely. And to do that, I need to get 3 parts in each picture. Well, I have an angle. I have an angle marker, I have a wall marker, and I can go after these angles in here, which are vertical. And I'm actually going to do that in my next line here. Let's see. Let's change colors. Let's go to just a black again. So I'm actually going to go after those angles. Let me erase the markers in the middle. So the smaller angles are these two. I'm going to go after those now. Those are vertical angles in the middle. They're very small vertical angles. So that's angle QRT. That's equal to angle WRU. And again, the whole reason there, line number 5, is it goes vertical. They're straight across from each other, a little funnel system. And now, as you can see from my smaller triangles, I have 3 marks in each triangle, the smaller triangles now. So on line 6, I can write that those small triangles are equal. That QRT is equal to the other small triangle, which is WRU. And the reason is by angle, side angle. Angle marker, side marker, angle marker. That's why the triangles are actually equal to each other, and that was, again, one of the acronyms we had on the other page. That's one of the few. And now that I know that the smaller triangles are equal, now I can say, these parts are the same. That's what I was trying to get to in the very end anyway. So let's name that off. So my final line here is to name on line number 7, this is the therefore line, ... that QT is equal to WU. And again, that was by CP, CTC. Corresponding parts of the smaller triangles are congruent. And that was the whole point of that proof. Now again, the reason why I picked this one is it's not just, it was 7 lines long, but we actually proved that 2 sets of triangles were equal. Because the bigger ones led to the smaller ones being equal, because I could talk about the individual parts. Now the only controversial step about this whole proof is what I wrote here to here. Because if you looked at letter for letter, I didn't write the Q and U being in the same locations. Q is in the front, W is in the back. But again, I could have switched them around because the 2 walls, all 4 walls were the same. So I couldn't visually tell, what letters to write in which order. So that was the only kind of tricky step that some people would have probably a problem with. Okay. But that was the whole entire proof. I just thought it was kind of interesting. I want to show you that. And it can kind of lead into what our next pictures are. So that's why I kind of picked it as well. Okay, so let's jump in. Let's keep continuing on with our notes. Okay, the next thing I want to talk about is some vocab terms before we move on to some of the new theorems today. On this particular picture, what we're looking at, this picture is an isosceles triangle. Let me write down the word isosceles. So, isosceles triangles. Now, again, the definition of an isosceles triangle is where 2 sides are congruent. Two sides are congruent. They're equal, right? So in this particular case, on an isosceles triangle, we call the sides that are equal the legs. Now we can mark those if you like, but those are the main parts of an isosceles triangle. That two walls have to match. Now the random third wall on an isosceles triangle, the random third wall that is different than the other two, is called the base. Now the base can be any length. It could be longer than the legs. It could be shorter than the legs. If it happens to be the exact same length, then it would be an equilateral triangle, and that would be, an equilateral triangle is an isosceles triangle, but it's special. It has all three walls being equal. But again, on a normal isosceles triangle, the base is the random third wall. Now, the other things that we have here are called base angles. Okay, these are called base angles. They're the angles that obviously touch the base. They can get real creative with the naming system. And then the last and final angle up here, this is angle number 1. This angle is actually called the vertex. It is different than the base angles. Okay, the vertex is across from the base. It doesn't necessarily have to be the biggest angle in an isosceles triangle. It doesn't have to be. It's the angle that is different than the base angles. It doesn't touch the base, obviously. So they call it a vertex. But these are the main vocab words that I wanted you to know from this picture, because we're going to actually use these words on the next couple of theorems. So you do need to know what a leg is, what a base is on an isosceles. And now, from the last couple days of notes, we've been talking about right triangles. You have the possibility of coming up with an isosceles right. Make that a little bit longer. You can have an isosceles right triangle where, two walls match in a right triangle. So then these would be the legs of a right triangle, which they are. They touch the 90-degree marker. And then this would be the base, or on a right triangle, it is also known as the hypotenuse. So, and then this would be the vertex, and these would be the base angles here and here. So we can still apply the same vocab terms if it turns out to be a right triangle as well. Okay, let's jump right in. Let's talk about our two theorems today. I'll let you write them down, and I'll talk about them out loud. And again, our sub can pause it. Okay, so this is theorem 4.10, isosceles triangle theorem. This is one of the main theorems that will eventually lead us on Friday to proving that the previous theorem 4.9 actually does work. We haven't actually proved that theorem yet because we needed this one. This one will actually lead us to it. So what this one says, the isosceles triangle theorem, it says that if two sides of a triangle are congruent, namely if you have an isosceles triangle, two walls match, as you can see I have the markers already on the picture, then the angles opposite of them, namely the base angles, that's angles 1 and 2 in this picture, so these are the base angles. What they're saying is that the angles that are opposite the walls would have to be the same. That's what they're saying here. Now, I do want to prove this one. I actually do want to show you that it does work and that it does use the acronyms that we've talked about earlier. But again, we are trying to prove that the base angles are the same. Okay. So now, to do this, I know it's going to seem a little strange. I'm actually going to turn one of these pictures around. I know that seems a little strange, but I'm going to actually turn this picture around just so we can mess with it. We can redraw. And I know that the labels are upside down now, but it's just easier to look at this. So I'm going to draw a line going down through the middle. Okay, and we're going to put this in such a way that it perfectly bisects this angle on the top. Okay, it perfectly bisects it. You can do that. You can put a protractor down, measure that top vertex angle, bisect that angle with a wall. Okay. And so we're going to make that a bisector, and we'll call this point down here, we'll just call this point P. I don't really care what that's called. So C to P, that's a bisector of an angle, so it's an angle bisector. Okay, so if we're going to do a proof of this, let's just do a flow chart so we don't waste all the time here today. So on line number 1 of a flow chart, again, we're going to do a flow chart to prove why those angles are the same. Line 1, we'd have to write what we're given. Well, we were given that, the wall A to C is congruent to the wall from B to C. We're given that, right? Those are the walls that were given. They're equal. It's an isosceles triangle. Line 2, now this is the part where it gets a little strange. We did a construction here. I drew an extra line on the picture that wasn't there. You were allowed to do that. I was allowed to take a ruler or a protractor and actually draw one of those. So we did an angle bisector. and again, I didn't even care where it hit that wall at the bottom. I didn't care that it hit P, in any specific spot. I just wanted to bisect angle C. So I drew angle bisector for angle C. Now, what that means in angle bisector, if we go back to the definition of bisecting, it means that this angle up here is the same as that angle. So on line number, on this, this is technically the third line of a flow chart, I'm going to write that those angles are the same. So angle PCB is equal to angle PCA. Those angles are the same. That's the definition of bisector if you want to be super exact. And then the other thing that I also have from this picture is I have the reflexive wall, right? The reflexive wall in the middle of the picture is the same. So that would be, my third line down here. CP is equal to itself. CP. Now I have 3 markers per picture, per triangle, because there is actually 2 triangles there if you can see them. I have the triangle on this side, I have the triangle over here, and they have 3 markers, and it does spell their correct acronyms. We have a side, an angle marker, and a side marker. So, and that is one of our acronyms that does say that these triangles are equal. So the left triangle, that is triangle PCB, is actually equal to the triangle PCA because of side angle side, SAS postulate. So I'm actually going to write that reason even though we don't write reasons on a flow chart. So those angles are actually equal, so side angle side. And now I can get to the parts about the triangles themselves. So since the triangles are equal, I can just jump to the chase and say that the parts about them are the same, namely that angle 2 is equal to angle 1. And that's what we were trying to prove on this one, because we were trying to prove that little thing. So that would be my last line. That angle 2 has to be equal to angle 1. And again, the reason would be CP, CTC. Corresponding parts of congruent triangles are congruent. This is huge. We needed this theorem to prove 4-9. I know it seems weird, because when you have isosceles triangles where 2 walls are the same, let me erase all these markers. Okay. When you have a picture that's isosceles where 2 walls are the same, the important thing about this that I want you to think about is when the 2 walls are the same, the angles in the corners have to be the same. We're going to use this on Friday when we do that Theorem 4-9 and we try to prove that. But this is big. Okay, let's move on to the last theorem of the day, and this is your last note. Again, we're not getting homework or anything like that today. Okay, 411. It's the converse of the last one. Converse, if you don't remember what the definition of converse was, we had this on the semester test. Converse is when you take a conditional statement and you switch the 2 parts around. So the last one, talked about that if I had an isosceles triangle, then the angles have to be equal. Well, this one says if I start with the angles being equal, then I can prove the walls are the same. Prove that it's isosceles. So it's the direct opposite of the last one. And again, this proof is actually the exact same proof as the last one I just did. But again, 2 angles of this triangle are equal. I want to prove that the walls opposite of them are equal. So I'm trying to prove that this wall and this wall, the wall that are across from the picture, are the same. So I'm trying to prove the legs are the same on this isosceles triangle. But again, we don't know it's isosceles. We're trying to prove that. Okay, so that's what we're trying to do here. Let me get a bigger eraser here. Okay, now I'm going to turn this picture. Apologies again. Yeah. All right, we're going to turn the picture. All right, just so it's easy to draw on. Now, again, how you'd actually attempt this, we're going to draw a line down through the picture, and how I did this, I drew this in such a way that it bisected the angle at the top. So if we're doing a flow chart proof, so again, a flow chart is basically a proof without putting all the reasons on it. So a flow chart, just get the idea of the outline of my proof. Line 1, or the first bubble I should say, is I would mark that angle 1 is equal to angle 2. That's the part that they gave me. That was the start. Ooh, angle 2. There we go. It's terrible. Angle 2. There we go. So they gave me that, and those are the markers that are on the picture. The second line is that construction thing where I actually did draw an angle bisector, because I can put a protractor down, measure angle E, and cut it in half. So I did an angle bisector of angle E, and so that forced the 2 angles to be the same. So on line 3, or third line, angle DE, and let's call this point down here P. So DEP is equal to angle FEP. So that's the markers I have up here. So these angles are the same. And then obviously, one of the things from the picture that is obvious, we have the reflexive wall in the middle. So that would be wall PE is congruent to PE. And now I have 3 markers per triangle, so I can actually prove that the 2 triangles are equal. And it is spelling one of the correct acronyms. So I could prove that the triangle DEP is congruent to triangle FEP. Again, this is a triangle symbol, sorry. It's terrible. There we go. And the reason why those triangles are equal is because of angle, angle, side. That was the abbreviation that actually proves that the triangles are equal, because angle, angle, side. So the triangles are equal, and if the triangles are equal, then we can say that the walls had to be the same. So I could say that DE, the wall, has to be equal to FE, which is what we're trying to prove. We're trying to prove that the walls are the same right here, which they'd have to be. These are the corresponding parts. They're the visual matching parts of the 2 smaller triangles. Okay, so again, it's the same exact proof as the last one, because it's almost the exact same wording. It's just I did the same kind of construction. Again, the part that really gets people is drawing the angle bisector. You are allowed to draw on pictures certain things. You know, I don't care where point P was down on the bottom. I just bisected angle E. I can put a protractor, measure it, cut it in half, and that doesn't affect the rest of the drawing. So that's why I was drawing that line down through the middle. Okay, that's it for today. That's all I wanted to cover. I just wanted to make sure that you had enough information for Friday, so when we actually start to prove Theorem 4.9, we can actually use these things about isosceles. I know that seems a little strange. Enjoy the rest of your day. I'll see you tomorrow.